I
Okay.
should introduce you.
Mhm.
It's a pleasure for me to introduce Kuntal Banerjee from Saskachewan, who is going to talk about very stable and wobbly loci for elliptic curves. And please, Kuntal, anytime you want.
Okay. Thanks, Marina, for the invitation and for introducing me to your research group. So let me begin with showing the picture that I have shown just a few minutes back. So this is the group picture that we took when we were together at Kelowna 2 years back in summer. And there are key people, relevant people of my life who are present in this picture. At first, Steve. Steve is my supervisor at Saskatchewan. I did my PhD under his supervision. And at extreme right, there is Ruxandra, my current postdoctoral advisor. And at extreme left on the front line, there is Marina, our host, or who invited me to give the talk, and Christian. Christian is one of the key people who are working on the very stable and the wobbly area in algebraic geometry. And here is me in the back line, in the middle. And this is Kuntal Banerjee. At that time, I was a PhD student. Now I am doing my postdoc at University of Waterloo with Ruxandra. So now let me go to my iPad. Okay. So as Marina has already mentioned, the title of my talk is very stable and the wobbly loci for elliptic curves. It is a joint work with my advisor, my collaborator, Steve Ryan. So let us go through some basic definitions. So we work with a complex algebraic curve or a compact Riemann surface, and we consider a line bundle on this compact Riemann surface. We call it the twist, and E on X is a holomorphic vector bundle of rank R. So once you have this holomorphic vector bundle, you can define a morphism between holomorphic bundles from E to E twisted by L. So this morphism phi is often called an L-twisted Higgs field. Okay. And once you have this phi, you can define many other morphisms and take their composition, consecutive composition. This will give you a morphism phi to the R from E to E tensored L tensor power R. So we call phi nilpotent if phi to the R is 0 and obviously if phi equal to 0, then phi is obviously nilpotent. But there may exist phi non-zero such that phi to the R vanishes. Okay. So once we have the definition of nilpotent L-twisted Higgs field, let us come to our main definition, semistability. So a bundle E to X of rank R is said to be an L very stable bundle if the only nilpotent endomorphism from E to E tensored L is 0. Okay. And if E is not L very stable, then we call E L wobbly. Okay. So this is the primary definition. So we can start creating some examples of very stable or wobbly bundles, which are quite elementary. So we can think about X is the compact Riemann surface of genus 0. And L is a twist OT where T is non-negative. Okay. Then any bundle E on P1. So I am assuming rank of E greater than or equal to 2 because we don't tackle the line bundle case, because line bundles are always, they are always very stable, because if you just consider the morphism phi, which is just taking value in L, and phi is 0, that means phi is 0. Okay, nothing to check. Then any bundle E which has rank at least 2 is wobbly. Okay, so it is very straightforward because on projective line we have the famous Barkov-Grothendieck decomposition, which makes our life simple. So to create the counter example, you can just, for the time being, think that R is 2. Okay, if you can do for R equal to 2, you can do for any rank. So in that case, E becomes OD1 plus OD2. So you can obtain either of d1 plus d2 plus t. This is non-negative, or d2 minus d1 plus t is non-negative, right? So if you want to write a phi, which is a global endomorphism, there will be four components in the global matrix, and you can plug these twisted morphisms on these empty places to create this phi. So I will use this common trick of making upper triangular matrices. So I'll choose some phi prime, which is in, it doesn't matter which one you obtain, which one of these inequalities you obtain to work. And I will place this phi prime here and 0 everywhere. It gives phi squared equals 0, but phi is non-zero. Okay. So it actually gives us our strategy of creating these non-zero nilpotent Higgs fields that construct a strictly upper triangular or lower triangular twisted bundle morphism. Okay. So this strategy actually helps us to understand these very stable bundles in terms of slope stability. So or slope semistability. So slope. So it says that, so our first observation is the following. Then we come to the slope stability stuff. That if E has a subbundle E prime and cosine bundle E double prime, that is E over E prime, so that H naught, that is the dimension of the endomorphism bundle from E double prime to E prime tensor L, is non-zero, then E is wobbly. The proof is simple and quite standard. I just write two exact sequence of bundles and it will be obvious. So there is the cosine bundle, and simply by tensoring you have another exact sequence of bundles, and here we can plug the non-zero morphism which already exists by our assumption in the result, I mean in the statement, and we just simply compose this morphism from E to M cell, and this composition morphism, call it phi, it always satisfies phi squared equals 0. So it will be important, but it is non-zero. You can verify it is elementary. Okay. Now this principle actually works to prove the following statement. So we consider the genus of X is at least 1, and the twist L has degree at least twice gx minus 2. So twice gx minus 2, that is the degree of the canonical line bundle on X. So if you have this condition, then a very stable bundle is always slope semistable. Okay. And even if you restrict your attention to the case where genus of X is strictly greater than 1, then E is slope stable. And if genus is 0, genus is 1, not 0. If genus is 1 and degree of L is greater than 0, then E is slope stable. So the principle is quite straightforward. If you have a destabilizing subbundle, then you can actually create this this diagram that I have drawn already. So these conditions actually give us very interesting ideas about very stable bundles as a collection inside the collection of stable bundles or semi-stable bundles. So this slope semistability actually helps us to accommodate the genus 1 curves. Okay. So let me write it as our motivation that fixed. This may be interesting for algebraic geometers. So this actually this is actually converging to the idea of a locus. Locus means something that has very good geometric properties, not as a subset, but some subvariety. Okay. So in case you have this genus greater than 1 and degree of L is at least twice gx minus 2, then the very stable L-twisted very stable bundles of ranked degree D that is living inside this moduli space of stable bundles, that is simply the isomorphism classes of stable bundles of fixed rank and degree. And if genus is 1 greater than 0, then also and now there is a marginal case where genus is 1 and Daigle equals 2gx minus 2, that is 0. In that case, we need to consider the polystable bundles because the semistable bundles do not construct a moduli space under isomorphism, right? We need to consider their strong equivalence. So we will consider the polystable bundles which are very stable. Again, we will call it as VRDL inside the moduli space of polystable vector bundles on an elliptic curve. Okay. Now, another definition. Anyone having any question? I feel it's good because we're straightforward.
No questions, and not even in the YouTube channel. So no questions.
Okay. Good, real good. So our definition that we used in our work with, me and Steve, in general, we considered this very stable locus to be the locus inside the moduli space of semistable bundles for any curve, okay? And this is called the very stable locus. And our wobbly locus is its complement inside the moduli space of semistable pairs. So let me tell you something about the definitions followed in the usual literature. So in the usual literature, as people are working so far, so L is taking to be the canonical line bundle. So in our work, we call it canonically twisted or canonically very stable, canonically wobbly bundles. Okay. So in that case, the genus of X is always greater than 1. That is the usual literature. And in that case, their definition is
Excuse me, may I ask a question?
please.
I'm a bit the very stable locus is empty when the twist is has degree greater than 2g minus 2. This follows from the Segre stratification.
I think so.
Well, it's proven actually. This is
okay.
Okay.
Okay. That
You're
is good,
focusing on genus 1. I'm not sure that's an exception, but are you focusing on genus 1? I'm sure
genus 1, yeah. Finally, I will focus on genus 1. Actually,
Okay.
for genus 1, we have actually proved that if I take 2 is greater than 2, there is no very stable bundle. Everything is wobbly. That is in our paper. Perhaps we'll not go through that proof in here.
Okay, so this may be a new proof. Okay.
Yeah. And thanks for the comment. So this is the usual definition, and this wobbly is the its complement, and sometimes they fix the determinant and consider this fixed determinant very stable locus. These steps are used by many mathematicians. For example, Paul and Pauli in their work about the wobbly divisors. So we'll stick to the definition that we have given here, and it is independent, harmless. It doesn't disturb any theory, and so following this popular definition that already exists in literature. So Lamont, in his first paper on global nilpotent cone, written in French actually, he attributed a result to Drinfeld, which says that the wobbly locus forms a closed subvariety of stable bundles of complex codimension 1. Okay, but there was no proof. Recently, mathematician from India, he has proved that it is true. In that case, they worked on this fixed determinant case. And Paul and Pauli, Christian Pauli, they together investigated the class of wobbly divisors in the Picard variety. Okay, and also there are more interesting results which are done by Anna and Christian, which actually involves that. So they actually invoke the Higgs bundles into the picture. So they viewed Phi as a global section of n times canonical line bundle, and they said that is very stable if and only if the restriction of the Hitchin morphism. So Hitchin morphism is the morphism that calculates the characteristic coefficients as the section of the tensor power of the twist. So the Hitchin morphism restricted on this affine space is proper if and only if inside this moduli space of Higgs bundles is closed if and only if this Hitchin morphism H is quasi-finite. So when I first started working on the very stable bundles on elliptic curves, my first target were to investigate these results in case of elliptic curves, because on elliptic curves we are not having this facility of stable bundles. We are going from stabilities to semistability, and to handle semistability we are working polystability actually. Okay. So this last criteria by Anna and Christian. So I have a new viewpoint. So we can refresh this result in a slightly different way. So see that this tangent bundle of rank of the moduli space of stable bundles, this lives actually inside the moduli space of Higgs bundles, and this is actually the fiber of the tangent bundle, right? Right. And this tangent bundle is actually forms an open subset. Okay, so this fiber is closed in this tangent bundle, but it is not necessarily closed in the moduli space of Higgs bundles, of semistable bundles. I mean semistable Higgs bundles, right? So closed in if and only if is very stable. So this actually gives us the idea of some work in elliptic curves that we'll see. Okay, and so I think I have already mentioned the base of the work that we are going to do. So now onwards we will fix an elliptic curve. Okay, and we just revisit some basic knowledge about elliptic curves. So stable bundles were actually present in Atiyah's work, but they were made explicit by Loring too in 1990s. So 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 bundles are actually always given on a based elliptic curve. That means that an elliptic curve with a base point. Okay. So the first observation is that moduli space of stable bundles, this is non-empty if and only if rank and degree are O prime, and when we consider the polystable bundles, we defined two new integers where H is the GCD of R and D, and each semistable bundle, if it is decomposable, that is okay. If it is indecomposable, then still it can be shown to be equivalent, strongly equivalent to a bundle of the form a stable bundle O times, tensor product with H many line bundles, where each of LIs has vanishing degree, and this bundle is stable. Okay. And this understanding actually gives us a very nice commutative diagram, which says that the symmetric power of the elliptic curve characterizes or parameterizes the isomorphism classes of polystable bundles. So there is a determinant morphism. So we just consider the determinant and then modify it by some power of the line bundle that always vanishes at A. And there is the Abel-Jacobi morphism, which I write as AJ. So there is a commutative diagram. Okay. And also this symmetric power of an elliptic curve, this is actually a projective bundle of a bundle on the Picard variety of degree H, that is X. And this finally gives you the semistable bundles, moduli space of semistable bundles with fixed determinant L, that is nothing but the projective space of codimension 1, which is the projective space of the global sections of determinant of E, or you can write it as simply as L. No, I'm sorry, not L. I mean L O times H minus D. Okay. So this actually tells us that the symmetric powers are going to be important in case of elliptic curves. Good. So let us look at some properties of elliptic curves. I will just quickly go through their properties, not go through explicit proofs. So first of all, it is actually defined in two ways. The product of H times acted by the symmetric group of H symbols. So we'll consider two elements, two tuples, H tuples, same, if they can be they can be changed into each other by action of a permutation sigma. Okay. Or there is another way that SimHX is the space of all effective divisors on X with degree H. Okay. And that projective bundle explanation works very nicely. So it is actually, the fiber is actually L and S. So at L in PKHX, the fiber is all the sections of L, and the symmetric power is this projective bundle. And very obvious, I mean, with a standard, right, that SimHX is smooth, compact, connected, projective algebraic. Of dimension H. It is not always true for surfaces, it is only curves, so we are fortunate. And there is a very nice covering map of degree H. And very vital that SimHX contains an open dense subset of distinct components. Okay, so these distinct components will actually give you the very stable polystable bundles, and where some components match, these are closed, and these will actually give you the wobbly locus. Okay. So why that is true? So you can think that SimHX, an element in SimHX can be written as direct sum of some stable bundles. Okay. So if I consider phi from AI to EI, so remember that the canonical line bundle is trivial. Okay. So is very stable if and only if EI not isomorphic to EJ for all I not equal to J. Okay, so I mean, if there is one I and J where EI isomorphic to EJ, then you can create something in the upper triangular or lower triangular block, right? And also another important point is that there is a non-zero global endomorphism between EI and EJ when they are stable of same degree, same rank. This is non-zero if and only if EI is isomorphic to EJ. Okay. And the wobbly ones, the wobbly polystable bundles, are those for which EI isomorphic to EJ for some I not equal to J. Okay, so this is the key information about understanding the very stable and the wobbly locus inside the Pauli space of semistable pairs. So now let us revisit some information about the canonically twisted Higgs bundles. So this is the PhD thesis work by Emilio Franco Gomez, and he was advised by Oscar, and their joint work was with Newstead. They published papers on that. And the main content about the stability and semistability of the Higgs bundles is that in case of elliptic curves, a Higgs bundle is semistable if and only if the underlying bundle is stable, and stable if and only if the underlying bundle is stable. Okay, so this actually gives us a very nice commutative diagram where the actions of SH, the symmetric group of H symbols, works very nicely. Okay, and also there is the Hitchin morphism. We can actually modify the Hitchin base by considering the repeated components to be same, and the Hitchin base will be if necessary, I will explain more, SimHC or C to the power H. And in this case, any fiber pi inverse, so if I define it as pi inverse of EI is closed. So the restriction of Hitchin morphism is proper, even if it is not very stable. It works for the wobbly points also. But in particular, there is one interesting feature about the very stable points is that if some EI is very stable, then this fiber has a vector space structure. So affine space. So the other results by Pauli and Anna, they work for these very stable bundles on elliptic curve. That quasi-finiteness works because once again we have proper morphism between two affine spaces. Okay, and now let us come to some kind of geometry of this wobbly and very stable locus. So I will not explain more on the proofs. We'll just see the results. So geometry of this wobbly locus that I was trying to do was some kind of mimicry of the work by Pal and Pauli. They were computing the class in the Picard group, I was trying to do fundamental classes of varieties. Okay. So in the wobbly locus, you can obtain at least two same component, or at least 3 up to at least h. Okay. So we'll call them standard wobbly loci, that is delta S. It is actually the image of a morphism. So the morphism is given by the diagonal morphism, which takes a point x from the elliptic curve, a divisor from symmetric power of x of order h minus s, and maps to sx plus d. Okay. And our s will run from 2 and h. And if you construct a very nice filtration of subvarieties, this delta 2 is our wobbly locus. Okay. And see that these are all, closed integral subvarieties. So delta is so this diagonal morphism was actually introduced by MacDonald, one of the co-authors of the famous commutative algebra book. And so this image of this diagonal morphism is studied by mathematicians. Okay, so I found something in the chat box. Oh, I see. Thanks, Anna. Thanks, Anna. I think we can talk about it.
Yeah, sure.
So this deltas are the closed integral subvarieties, and the symmetric power of x at power h. This has dimension h, right? So that means all these delta s must have dimension. You can think they're Kral dimension, even if they are not smooth, as h minus s plus 1. Okay. And in particular, dimension of this wobbly locus is h minus 1. Okay. That means it is a closed subvariety of codimension 1. That was the version of Drinfeld's claim. Drinfeld claimed that it is closed subvariety in the moduli space of stable pairs. Okay. So we are just looking at the version on the elliptic curves, and we are seeing that these are forming a closed subvariety of codimension 1. Okay. And the very stable locus, that is V2, that is sim hx minus delta 2, that is definitely, open dense subset. Naturally, we have already said it is open dense subset. Okay. And a few more things, I think then I can stop. That if someone asked me about fixing determinant delta, I mean determinant of the bundles to be this L, then still we can define this this wobbly loci of fixed determinant L, it is inside a projective variety, that is the projective space of dimension 1. And in that case, it is restriction of the same diagonal morphism on a new variety, which is actually a projective bundle let me fix my notations. From L1 to PH minus 1. So this EL1 H minus S, it is a bundle on X, which maps, which is fiber at each X, the sections S, make it big S, so that S is a section of some L1 times okay. If you ask me, then I will explain it in detail. Okay, and also then we obtain that there is a very nice filtration of subvarieties, which says that is actually of dimension H minus S. So this bundle is of rank H minus S. So its projective bundle has dimension H minus S. Okay, and in particular, if S is 2, that is H minus 2, that means it still is of codimension 1 inside PH minus 1. Okay, so I think this is the way we proved the claim of Drinfeld in case of elliptic curves. And then I also had some information about their fundamental class. If Marina allows me for just 2-3 minutes, then I can.
Of course.
So this delta S and this delta LS. So these are subvarieties in the symmetric power of X and the projective space of dimension H minus 1, right? So you have the right to ask their fundamental classes. So McDonald actually computed the fundamental class of this delta S. These are now very standard. I imported their results from our I took the results of McDonald and pasted in my in my article. So this fundamental class of delta S is actually, I will explain the expressions. Where eta and sigma are inside. And this eta and sigma follow some equalities, and sigma square vanishes and the fundamental class is computed by this. Okay, and then this delta LS, it is actually intersection of this delta S with pH minus 1. Okay, so its fundamental class will be the product of that is inside as a subvariety of symmetric power. Okay, and this is actually computed as SH times eta power S minus 1 times sigma. And finally, you can pull back this eta and sigma on P1. So you can write this this I star pullback of sigma as m of a, m times a, sorry, where a is a generator of this integral cohomology group, and that says that eta star this is either 0 or same as ma. Then you just plug it there. SH same. M to the power is a to the power is. So A is a fixed generator of this second integral cohomology group of pH minus 1, and M is some number. So M is some number such that I star that restriction of sigma is M times A. Okay. So these results, this computation of fundamental class of this fixed determinant wobbly locus, that is actually not present in our paper, but I think I have accomplished this with time. So thanks so much for listening to me, and please, if you have any questions.
Thank you, Kuntal. Thank you very much. Are there questions there? Not in YouTube. I thought you have some people there, but they don't seem to have any question. But
I want to make a question. Since you are computing the classes of this wobbly locus and its possible components, for example, do you expect many components? For example,
no, actually these are irreducible subvarieties.
Sorry?
These are irreducible because actually these deltas, I mean delta S, these are actually obtained as image of a holomorphic map.
Okay.
And the domain of the holomorphic map is itself irreducible variety. Symmetric powers are always irreducible, right? So these are actually irreducible. Irreducible complex analytic varieties, projective algebraic. So there is only one component.
Good. Okay, thank you.
Okay. I have a couple of questions.
Please.
Is it possible to understand the automorphism of this very wobbly, I mean, of the points in the very wobbly locus and so on?
Okay, so let me share my thought with you. So to be very frank and very precise, I still do not understand this topology of wobbly locus enough, because at first when we started working on it, we were actually puzzled by a mistake by McDonald. So McDonald first said that this delta S. So let me write. So McDonald in his paper kind of claimed that delta S is actually isomorphic to this x times sin h minus x by this pi s. That is actually wrong, absolutely wrong, because if s equals, say, h over 2, you can choose h an even number. This pi s is not even injective. Okay, so
Okay.
in some cases, if s is in between, h and if it is greater than this floor function of h over 2,
Mhm.
then this becomes a homeomorphism actually. But I do not know if it is going to be a biholomorphism. I do not know that. So if that happens, then everything is controlled by this stuff. Okay, but otherwise it is quite difficult to understand.
I see.
Okay.
I see. Thank you very much. Any more questions?
So I am seeing a direct message from Anna about
Okay.
she's
It's-
praising me. Thanks so much, and also about something about the postdoc that she has floated. So I think Anna has left, but I would like to reply to her. I think I should type an
Okay.
email to her sometime.
Okay. Well, if you want to reply here,
I can reply here, but I don't know if Anna will be able to see it because I think
I see.
she's
Perfect.
already away. She has left, I think.
Okay, you're right. Actually, I have a message from her that says that she has to go to a meeting, university duties,
Yeah.
and she had to leave. Okay, to leave. Thank you very much. Let's thank Kuntal.